Okay, Ben, so you can start. I will give you a 5-minute warning.
Great, thank you. Can you see the slides?
We do.
Fantastic. Okay, great. So yes, I'll tell you about how we can use measurements that use all the available information, and I'll lead up to a new technique that we call OmniFold. Let me click on here. Great. So I think many of you, of course, are super experts in the workflow of data analysis, simulation-based data analysis in high energy physics. So you've seen, you probably visualized charts like this, where on the right-hand side here, this is sort of the flow that we have in our experiment. You know, when we want to learn something about nature to do inference, and for that we build experiments, we do some dimensionality reduction, and then on the left side, we try to emulate the same kind of thing in a simulation where we have our theory, which we want to infer something about, and then we have some simulators, then we apply the same kind of dimensionality reduction and comparison in order to do some inference. And as you've seen all throughout this workshop, machine learning and deep learning in general have made a huge impact, or making a big impact on all aspects of both chains, on both the data side, so on data processing and data curation, as well as on the simulation side, where you can use neural networks to speed things up, to enhance classification performance, and many other tasks. But today I want to focus on this one box that says parameter estimation / unfolding, and how we can use simulations and scaffold them with machine learning, with neural networks in particular, to use all the available information to learn something about underlying theory. Okay, and so the backdrop here will be that, you know, sort of in low dimensions, if you want to do inference, you can often just build a probability density. So I have some parameters I want to learn something about. I have some feature space X, and if I can construct P of X given parameters, I can maximize my likelihood, and that's great. The problem though is that if X is high dimensional, then P is intractable. I can't write down P, and so I can't, in principle, you'd think you can't do direct maximum likelihood. Okay, so I call this the hyper challenge, and it's both the challenge and an opportunity, because we're trying to learn something about a high dimensional phase space. So whether that's, you know, in a collider context like this image would show here, or any other context where the number of degrees of freedom is very large, and then that's combined with, say, a data volume that's also very large, because our detectors are becoming more complicated, and so you can think of them like sort of hyperspectral cameras, where there are many redundant channels, and we're trying to infer something about the underlying physical phase space from this high dimensional data space. And so combining these together gives us really a high dimensional challenge. Okay, so let me give you, I'm going to work up to an example, which I think is really sort of stresses the idea of inference to the extreme, where the parameters we want to actually estimate are basically all the degrees of freedom. And so the way to think about this is, if you imagine some collider event, although it doesn't have to be a collider event, it could be any kind of event where you have some particle phase space and then some detector phase space. So we want to infer something about the particles before they hit our detector. And of course, we only measure the detector stuff. So these are kind of schematic diagrams that show particles produced on the left, on the right, sort of like signatures in our detector. And this is sort of akin to removing detector distortions, because once you remove the detector distortions, you've basically gone back to the particle phase space. Okay, so one way of doing this would be maximum likelihood. So I could just say, okay, my unfolded distribution, the one that has the detector effects removed, would just be maximum likelihood. I find the true that maximizes P of measured given true. And this P of measured given true is sometimes called the point spread function, sometimes it's called the response matrix. But the problem here is that I'm talking about a case where measured is hyperspectral, true is hypervariate, and so P of measured given true is intractable. There's no way to write that down, and so direct maximization of the likelihood is impossible. Okay, however, the whole point of this talk, sitting in the session, is that we have simulators, and we can sample very effectively from P of measured given true. And so I'll tell you now a story about how we can do simulation-based or likelihood-free inference. Okay. So there are a lot of ways to do likelihood-free inference. So that is to say, do maximum likelihood without actually writing down the likelihood function itself. But let me give you one example, and it's going to be based on the technology of reweighting. So I'm sure many of you are familiar with reweighting, but let me just briefly review it. The idea is that I have two samples, one sampled from P and one sampled from Q. And if I learn, my weights would be, say, Q over P, so that if I have a sample from P and have a sample from Q, if I apply the weights to the sample from P, it will look statistically identical to Q. Any statistic you compute will be within the uncertainty the same. Okay, So that's great, but I just told you that I can't construct the P and Q because the likelihood is intractable. How can I possibly get W? And the answer is that there's a fact, which is that neural networks learn to approximate the likelihood ratio or something related to it in a known way. And so basically you can use neural networks as likelihood ratio approximators. And you can turn the problem of density estimation into a problem of classification, which is great because it's much easier. And so the solution is to just simply train a neural network to distinguish the sample from P and from Q, and then interpret the neural network output itself as a likelihood ratio. And so, yeah, this really can dramatically change how difficult this regional problem is. So now I'm going to spend the rest of the talk discussing how we can do this in practice and kind of the applications. Okay, so the recurring example I'm going to give is our collider events, although in principle could be anything. The collider example, I think, really shows the power of this method because there are a lot of particles in a given event, so that's a lot of degrees of freedom, and there's a variable number of them. So it's hard to make a generative model where you have variable number of outputs, but classifying that is easy and relatively easy. And the third thing is that there's a lot of symmetry. So for instance, all the particles are exchangeable. There's nothing special about their order. And so building in symmetry to classifiers is easy, but building in symmetry to generative models is much harder. Okay, and the context here is that we want to do reweighting on the full phase space, so all the particles and their type. And the neural network architecture that we're going to use is called the particle flow network, which is basically a deep sets variant. And deep sets is a very clever neural network architecture that basically acts on sets, so it's permutation invariant, and it can take variable length inputs. And there's some really beautiful papers down here at the bottom of the screen if you want to read more about them. Okay, but just to stress here that when I say full phase space, really at the end, we're able to have a new simulation that has all the information that you could possibly measure, and it's statistically indistinguishable from the original one. Okay, so it's pretty difficult to visualize what it means to reweight a variable length high-dimensional phase space. So the best we can do is we can project down and look at some observables to make sure that they work. So here's an example where we have some E plus E minus collisions in simulation. We've done some full phase space reweighting. We have two different simulations, reweight one to the other, and then we can check a bunch of observables. So here we have data set 1 and 2. Those are the blue and black. And then we've reweighted data set 1 with weights so that it should look identical to data set 2. And so you can see that the orange and the black dash, they agree for these two observables. It doesn't matter as much what the observables are, but you can compute any observable, and we've checked all the ones we can think about, and they basically, they agree. So we were able to morph data set 1 and data set 2 using this classification for reweighting procedure, which we call DOCTOR. It stands for Deep Neural Networks Using Classification and for Tuning and Reweighting. Okay, and actually it works even for very subtle perturbations. So this is probably the most technical slide of the talk, but I just want to say that, so here we have we generate events using the simulator Pythia, and there's some parameters you can tune in Pythia, and that's how we generated the two data sets. I wanted to show that we can reweight one to the other. And the point is that the left column here represents where we change one parameter in Pythia. It's related to hadronization. And it has basically changes everything, but only by a little bit. And these histograms, these plots you see are ratios of the weighted to unweighted. And you can see that the orange here is the weighted sample 1, and it's just spot on. So it should be 1 if the reweighting is effective, and the blue is before reweighting. And you see the blue is everywhere a little bit different from 1, but the orange is really spot on. So this reweighting is able to really identify the small deviations all over phase space. And the right is an even stronger test where we only change the probability for generating strange hadrons inside a parton shower. And this should basically affect nothing except for things related to the strange particles. So you can see that basically the neural network has learned to ignore everything except for the number of kaons. And it said, oh, the number of kaons is different in these two samples. Let's reweight that. And just doesn't affect anything else. So the whole high-dimensional phase space, it's like picked out just the kaons and made those different, which is pretty amazing. We didn't tell it about kaons. It just learned to do that automatically. All right. Of course, this can be extended. So if you have just two samples, I told you how to do the discrete version. But now imagine you have some parameter. I mean, at the end of the day, I said you want to do inference. So if you have some continuous parameters, theta, then you could simply learn a parameterized classifier. So the reweighting function, which is a classifier, can just be, you can just learn to interpolate between different samples. And this is basically as trivial as adding the parameter as a feature in the learning, and then providing many examples with different values of that parameter. And so we showed this is effective. For instance, if you modify alpha s in the simulation, that also changes the phase space. And this plot here shows a chi-squared per degree of freedom for particular observable. Doesn't matter what the observable was after doing this full phase space reweighting. And you can see that we had a target value of alpha s equals 0.16. And that's the unweighted and weighted agree there by construction. And then as we move away, the unweighted becomes very different than the weighted, but then the weighted is basically spot on 1. So the reweighting worked very effectively everywhere. And then you can use this technology to actually do parameter estimation. So once you have a continuous reweighter for a given set of parameters, you can then use data and fit basically this model, do maximum likelihood, without ever actually constructing the likelihood itself. And the way you do that is sort of shown symbolically on this slide, where you have some reweighter function W, and the reweighter function takes as input the features and the parameters. And then, so the second line here is the reweighted simulation, and the first line here is the data. And basically one idea is that you can train a classifier to distinguish data and simulation, and simultaneously change the simulation based on the reweighter function. And you can think of it like the reweighter function continues to tune the simulation using the reweighting function until the classifier can't distinguish data and the reweighted simulation anymore. And then you've succeeded in tuning or in estimating the parameters data. And turns out that's very effective. Here's a plot that just shows that you can do gradient descent this way. So we started with some initial parameters here in red, and we ran this procedure using the reweighting down to the target value, which is in green. And we actually did it's a 3-dimensional function, and this is just a slice of that in the loss landscape. And the x-axis here is the alpha s value used in the simulation, and the y-axis is this hadronization parameter that we modified. And so this shows that we can do this learning, basically maximum likelihood on the full phase space using all of the information. So this fitting here is basically using many hundreds of particles, and it's a variable length. So I can't tell you exactly what the phase space is because it's variable length and all their particle information. Okay. But I came here to talk about unfolding, which I think is like I said, stressing the inference problem to the extreme. And so here's kind of a picture of where I kind of started, where parameter estimation is I go from my detector data and I want to learn something about parameters of my model. But unfolding is saying I want to remove detector distortion. So basically my target is not parameters of the model, but all the particles themselves. So the pre-detector components. And I'm going to show you how we can achieve that with maximum likelihood without ever writing down the likelihood by using iterative reweighting. Okay. And we call this algorithm unfolding by iterative weighting. I call it OmniFold. And it's a little bit complicated and it works iteratively. So let me walk you through it. The idea is that we want to learn something about the top right box. So that's the true pre-detector phase space. Of course, we only measure the top left box, and we're assisted in this task by the bottom row. So we, of course, have a simulation which has both the pre-detector part and the post-detector part. And so we're going to use the bottom row to do the black arrow in the top row. So it starts with one reweighting step, or we reweight the detector level simulation to the measured data. And that gives us a set of weights. And per example in the simulated events. And then we can pull those weights back to the pre-detector part, the generated level. And because for a given event, we have both the pre-detector part and the post-detector part. So if you have weights on the detector part, you obviously also have weights at the pre-detector part, the particle level phase space. Now, the challenge here is that those weights are not a function of the particle level phase space. They're a function of the simulated phase space. And so you could have, for instance, you could have two events that are exactly the same particle level phase space, different detector level phase space, and therefore have different weights. So that's not desirable. We want to have a real function of the particle level phase space. So we have a second step. And the second step, you learn to reweight the pre-detector part to itself using these weights. So you have one set of events that have the pulled back weights and one set of events that don't have any weights, and you learn a reweighting function from one to the other. And you can think of that as sort of like a smoothing step, and that then learns a proper reweighting function on the particle level space. And then once you have that, you can, of course, then push the weights back to the post-detector part, and the whole procedure can repeat many times. You can pull back the weights, push forward the weights, and then at some point you stop, and once you stop, you have a set of weights for the pre-detector part, the generated level, and that will be your best estimation of the truth. All right. So now let me show this works with plots. So once again, this is sort of a collider simulation. So it doesn't really, I have to pick one observable to show you how it works. So here's an observable, it's called n-sub-jettiness. It doesn't matter so much what it is, but the point is that it characterizes how two cluster-like or one cluster-like an event is. So if you're on the left, your event has sort of two nodes of energy, where if you're on the right, you have one node of energy. And the green here is the truth. So we have two simulations. One will be called the truth, one will be called data, one will be called simulation. And so the green is the truth. And we have a simulation of the detector. So that's like our data, and that's the black. So the detector distorts the green to the black, and we want to go from black to green. That's what unfolding would do. And to aid us in this task, we have another simulation, which also has a pre-detector part, which we call gen. And you see the blue and the green are not the same, and that's okay. We know that our simulations are only approximations to nature, so it's not so surprising that our simulations are not exactly the right answer, but that's okay because we also have a mapping to detector level. So the orange here is the detector distortions from the blue. And as long as the distortions are modeled well between blue and orange and green and black, we can use the mapping between blue and orange to infer the mapping between black and green. And one sort of standard unfolding technique is called iterative Bayesian unfolding, which is one of the most widely used in colliders. And that is basically a binned regularized matrix inversion. And it does fairly well. So you can see here, using this unfolding, the gray is pretty close to the green. In the ratio, you see it's close to 1. Now this approach basically requires, it's done per observable, it's binned, and it's binned. Whereas we can do OmniFold, and OmniFold is unbinned, and it's for the full phase space. So to make this plot, we've binned it and picked a particular observable. But of course, we actually have any observable we like. And you can see that the red in the ratio is actually closer to 1 than the gray. And that's because OmniFold has access to more information than the gray one does. So the gray one just has access to this one observable, whereas the red sees everything. And so anything that actually affects the detector response, in principle, the red can use to do the unfolding. And so that's why it's more effective. And as I mentioned, actually, with OmniFold, you get all the observables you like for free. So here are many observables. It doesn't matter really what they are. Some of them are like the mass of the event, some of them related to the number of particles in the event. And we have all the same lines. So there's the truth, the actual truth, the data, and then the simulated truth and the simulated data. And you can look for each one of them in the ratio plots. If you just look at those, there's a gray line and a red line. And the gray line is the one-dimensional bin version applied to that particular observable. And the red is OmniFold. So for gray, there are 6 different gray ones because we had to do, those are binned and you have to do one at a time. Whereas for the red, we did one OmniFold, and then we compute the distribution. And so you see the red, if you just look at all the ratios, is basically nowhere worse than the gray. And it is just 1. There's only 1, and once you have it, you can compute anything. And of course, you can rebin later because it's unbinned. So, so just to stress, OmniFold here is unbinned. I think that's pretty clear from its construction. It actually approaches the maximum likelihood estimator. I didn't prove that to you, but if you're curious for the technical details, you can check out our paper. It turns out that this iterative procedure actually approaches the maximum likelihood estimator on the full phase space. It is full phase space, so that is to say that you can compute whatever observables you like after you've done one unfolding. So you don't have to decide on the observable ahead of time, neither the observable nor the binning. And in fact, it not only gives you access to the full phase space, but it also improves the resolution from auxiliary features. And that I showed you earlier. And it's because OmniFold has access to everything. So anything that would affect the resolution of the detector resolution, in principle, OmniFold has access to and can use when doing the unfolding. And so in this way, the OmniFold procedure is really a powerful method to give access to the pre-detector phase space.
5 minutes.
Thank you very much. Yeah, I'm at the end. Okay, so now to give just a brief overview of all the techniques I've told you about today. So today I've given you a taste of full phase space and likelihood-free approaches to do inference. And so by full phase space here, just to remind you, I really mean all the measurable information. So in the collider context, that was all the particle 4 vectors and their flavor, but that could mean really anything. I mean, whatever attribute you have for all the data observables. I showed you how to morph one simulation to another. That was a discrete reweighting. Then how to do continuous morphing, basically by learning a parameterized classifier. Then you can do parameter estimation, maximum likelihood basically, by using this continuous reweighting function. And lastly, I showed how you can iterate the reweighting procedure to do unfolding, which is sort of doing inference on the full phase space. All right. And so that brings me to the end. So I think I don't need to tell you, you're all here learning about learning and presenting about machine learning. So of course, I think it has a great power to enhance, accelerate, and empower our analyses. And I think that one of the biggest advantages that deep learning in particular gives us is it allows us to access the full phase space of our experiments to do inference with all the available information. And one way of really exploiting those precious data is to use the simulation to make the best use and perform inference using optimal and high-dimensional methods. So I think that's it. Thank you very much.
Thanks, Ben. That's very impressive and seems more advanced than what we do in analysis field so far. So if you don't mind sharing the webpage, and let's see what
and
kind of
while
questions.
he's doing that, I can read off the first question.
Sure.
Can you explain how you applied the trained network to reweight samples? What's the relationship between the weight function and the network output?
So is it better to share the questions or my slides?
Ideally,
that's up to you.
both.
Yeah, ideally both, but you can do whatever.
Yeah, okay. Well, let me just go to that, I guess, just a second. Okay, it should be quick to toggle anyway. All right, how you apply the trained network to reweight samples. Right, so yeah, this is a good question. So this depends, it actually turns out it depends on the loss function. So for instance, if you use like a binary cross entropy, which is I think everyone's favorite, or the mean squared error, it turns out that your neural network basically learns P of class given data. And so if you want to turn that into P of data given class, which is what you actually want, it's just a simple, you use Bayes' theorem. And so you can show that if you train with cross entropy, that let's say your output is like binary cross entropy, and let's say your output is like F. And then it turns out that F over 1 minus F, so that simple monotonic rescaling, is actually proportional to the likelihood ratio. That is to say, P of X given class 1 over P of X given class 2. And so for a given loss function, you can derive analytically what the relationship is between the output and the likelihood ratio. And then it's just a simple arithmetic to take your neural network output and then just do a transformation. Like in this case, like I said, it's F over 1 minus F, and then you have your weights. Okay.
Right. Next question. How computationally intensive is the iterative reweighing in OmniFold?
Yeah, so one of the really nice features about this is that it's a classifier. So if any of you ever tried training a generative model, that's way harder than training a classifier. This literally just takes 2 samples and trains a classifier, and how difficult it is for each iteration depends on how complicated the classifier is. So if you really want to use the full phase space, then it's important to use neural network architectures that are basically well matched to the data type. So in this case, like our data are variable length sets. And so we use these deep set architectures, and those are very effective. And it turns out because they're well matched to the data structure, we didn't have to do basically we did very little hyperparameter optimization, and the networks train pretty effectively, even for these like high dimensional variable length structures. So, and in part because they're parameter efficient. So if we had trained instead on like a fully connected network using the full by zero padding and all that would probably be much less effective. But in this case, it actually was not so bad. All right, so the next question was...
A new question just came in.
Oh, yeah.
Let me highlight that.
Ah, okay. Yeah, so it says, can you give an example of what data sets you use for each step? Do you do the SIMS versus generated transformation on some calibration control region? Right, so here, for a given step, you have you have two data sets. There's like the data you want to actually infer about. Then you have a simulation, which is supposed to be as close as possible to that data. And then the simulation should have both the pre-detector and the post-detector part. Because if you have a detector simulation, obviously you have the part before the detector simulation also. And so there should be a mapping between, there should be an ordered set. So you have one data set that has both pre-detector and post-detector part, that's from simulation, and then you have the data, which you want to learn something about. And yeah, it might be possible to do this where you sort of replace part of it with some calibration data, but the way we envisioned the initial algorithm was that you have a simulation of exactly the data you want to learn something about.
We don't have any more questions. We do have a few more minutes in case anybody does come up with one, but yeah.
I'll take the privilege as being one of the organizers to ask you, Ben, do you have any, you said you could talk about uncertainty quantification. Do you want to just give a couple of minutes on that? And if you were there for Igor's summary, I don't know if this ties into that at all. I don't know if you know anything about Bayesian networks.
Yeah, so I did see Igor's summary, and I think that I know a lot about Bayesian networks. I think they're a very interesting tool, and I think that one challenge that we have is that our uncertainty quantification usually has multiple components, and I think that Bayesian networks are very effective at estimating what I would call the statistical uncertainty, which or component of the statistical uncertainty rather. Whereas there are other aspects, of course, and I think in general, some systematic uncertainties can be dominant. And I think that Bayesian networks are probably less able to quantify exactly what that means. But in any case, yes. So for here, doing any simulation-based inference, there are challenges related to uncertainty. So you have to have an uncertainty. There are various components of uncertainties. So there are uncertainty on the fidelity of like estimating likelihood ratio. And so that's sort of an uncertainty on the method. And then you sort of have uncertainty on the bias of the result based on how well your simulation matches the data. And in particular here, what's most essential is that your detector simulation is a good model of the data, of the actual detector. And something that I've thought a bit about is how do we get uncertainties, high dimensional uncertainties? So there was something that I think it was briefly mentioned about, like, you could have uncertainties where you could jiggle all the inputs within their uncertainty and then propagate that through your network. And that would be great if we had the full uncertainty model. So if you imagine I have some feature space X, P of X would be like my uncertainty. If I had that full uncertainty model, that would be great. But often we don't have that, right? So we'll have some uncertainty on some aspect of it. So, I know like the energy I calibrate the energy of some particular part of my detector, and I know that very well. And if that factorizes, so if I have multiple objects in my final state, and I have the uncertainty on each one of those, and they're all independent, then we can build this high dimensional uncertainty model, and that's very effective. But imagine we can't do that. So in general, the uncertainty model doesn't need to factorize, and that I think is probably the biggest challenge to deploying in practice methods that require extrapolating. So in this particular case, I think that depending on how you set up the problem, I think that for the moment, the best way to approach sort of like using these kind of simulation-based methods is to use final states for which the uncertainty does factorize to the best extent possible. And I think that there are some methods for doing not factorized uncertainty. So for instance, we wrote a paper recently where we used adversarial examples. So from there's like a field of machine learning called AI safety, which we tried to borrow some techniques from to sort of bound the possible high dimensional uncertainty. And that doesn't give you any statistical uncertainty, or doesn't give you a statistical uncertainty, but it gives you a bound on what your worst case uncertainty might be. And I think tools like that might be effective.
Thanks, Ben. We can talk about uncertainties as physicists forever, but
yes.
Let's thank Ben again, and let's come back to the agenda.